now we're going to talk about electric dipoles. An electric dipole is any two particles of equal but opposite charge, or we'll just say opposite but equal charge, fits better in the blanks, separated by a distance d. I forgot a little blank there. So it can be any arrangement of charge where you have maybe a negative here and a positive here, and then there's like this distance d between them. So this whole cluster is called a dipole. It's called a dipole because it has two poles, you know. So that's kind of the way it looks. This can be very small, two elementary charged particles, or it can be like literally two charged spheres separated by a meter. So either way, it's called a dipole. And when we study this object, it's kind of like studying an atom versus, you know, a single electron or whatever. So, you know, when we think about the hydrogen atom, right, we don't really think about like, oh, there's a proton and there's an electron. We think, oh, this is a hydrogen atom. So we think of it as a unit. And we like to think of this dipole as a unit. So in other words, even though this contributes a field from the electrically negative side and a field from the electrically positive side, we like to just think of this thing as a cluster and then just ask what field does this whole object give in general. And we'd like to do this with as many objects as possible. It'd be nice to know, you know, how to deal with like a tripole. You know what I mean? Like if there's an equilateral triangle of charge, maybe two negatives and a positive or vice versa. Like how would you think of a tripole? Like what does its field look like in its neighborhood? So even though it has subconstituents, we want to think of it as a single object. Okay, so it's a little too complicated for us right now to study the field everywhere. Let's study along this line. Okay? All right. Oh, and by the way, something we will need later that is not important now. Let's fill in this second line. It's just a little vocab thing. There is a little vector called P, and it's the electric dipole moment vector. Its magnitude is QD. Oh, I already wrote that. Its magnitude is QD. All right. Q is the charge of either end. They're both the same charge. So you just take one of the charges times D, and that gives you how much magnitude P has. And it always points from the negative end to the positive end, which kind of flies in the face of the idea that fields point from, you know, out of positive things. But it points from the negative end to the positive end. So I don't want to say too much about dipole moment right now, but just like, for example, if this is the negative end and this is the positive end, the dipole moment would be pointing this way. It's not a field vector line. It's a totally different thing. In fact, it doesn't even have the same units as field because it's found by doing Q times D, right? Which gives us newtons times meters. So anyway, I don't want to focus too much on that thing, but that thing will simplify our life later. Right now, let's go back to our dipole. And let's talk about the the electric field set up near this dipole. Now, where do we want to stand? Well, if we stand between the charges, that would be interesting. But frankly, if this is a very, very, very tiny dipole, we might not be able to do that. So let's stand on the line somewhere else. How about over here? Okay, so when we stand over here, we experience two fields, one from the negative Q charge and one from the positive Q charge. Okay, so let's first look, let's just call this charge 1, and then we'll call this charge 2. Let's look at charge 1. What is the field set up by charge 1? Well, first thing we need to understand is it's going to have magnitude KQ over R squared. KQ over R squared. And technically it's a negative Q, right? So that means it's going to point, all of the field vectors that it produces, all of them, all the field lines, point towards itself. We talked about that a while ago. That means the one that's on our black line literally points, to the left, towards the negative charge. Okay? All right. So that means we would need either a negative. There's two ways to think of it. We're not really doing like the cos theta sine theta two-dimensional on this, but you can put a negative here for one of two reasons. One, that arrow is pointing to the left, and left is, negative. Or the charge is negative, and therefore it reverses the r hat. Or r hat is pointing to the right, but the negative pulls the field the other way. So either way, that field line is to be drawn to the left, therefore we're putting a negative. Okay, and then the r is tricky. The r is tricky because r is the measure from where we're standing to the charge. So how are we going to figure that out? Well, we need to pick a distance that is meaningful. So I'm going to start at the center, and we're going to measure everything from the center. So going this way, we'll call this distance z. So we're standing z units from the center of the dipole. Okay? And then we know that the center is, of course, d over 2 away from the endpoints. So I'm kind of rewriting this. The red segment is length d, but is broken into d over 2 on the left and d over 2 on the right. So how far are we really from the first charge, 1? We're a total distance of z plus d over 2. See that? Okay, so the bottom, I'm going to actually upgrade that to z plus d over 2 quantity squared. So it's z plus d over 2 quantity squared. Now let's look at charge 2. Charge 2 is a different story. Okay. Partly because the field lines are to be drawn away from positive charges. So now I'm drawing a field line pointing away from positive charge. Okay? Now, because we're standing closer to this charge, actually, we experience a larger magnitude of it too. So, in a sense, the field we sense from the positive charge is more influential than the field we feel from that more distant negative charge. So that'll take care of itself, but we just have to understand this is pointing to the right, and it's a positive charge anyway, so you would have gotten a positive either way. And then the distance is a little different this time. Now the distance is a total of z minus d over 2. So I'll highlight that in yellow. So this total distance is z, but this part is d over 2. So the part right here is yellow minus yellow. So it's z minus d over 2. Z minus d over 2. Okay, so now we're going to combine the two fields and add them together. So our net field is going to be, my pen got a little thin there, let me change this thickness. There's that one, which is from the negative charge. And then we have the other one, which is from the positive charge. I'll write it first, though, because I like to have the minus between the fractions. So this is like E2 plus E1. But I wanted the minus in the middle. Okay. So it's written as E1, E2 plus E1. Okay, so now we've got to simplify that thing, because I have a funny feeling that if we do simplify it, we'll be very glad we did. We might even find that the vector I mentioned earlier, the little moment vector, pops up in our work. So we might find a couple little QDs floating around, and if we find a QD, we're going to call it P in general. Okay, so the rest of this is very complicated, so you can watch this and just kind of sit back and kind of watch it happen. All right. So this is also in our textbook, but it's not copyrighted. This is the magnetic or the electric field of a dipole, so nobody's copyrighted that. All right, here we go. We have to combine these fractions. All right, so the first step I'm going to do is I'm going to pull out the KQ, obviously. So I have KQ, and then I have 1 over z minus d over 2 squared minus 1 over z plus d over 2 squared. Okay, now I don't like how it has fractions within fractions. I don't like any of that kind of stuff, complex fraction stuff. But another thing I hate, I was speaking of the solution there, another thing I hate is just the fact that I don't have this field set up where z is sort of the important distance. Like everything's like z minus d over 2 and all that stuff. That's complicated. So what I'm going to do is I'm going to make sure there's a z squared on the bottom of this problem when I'm all done. Remember, the bottom distance squared represents the distance to the object. Since our object is the dipole and our distance to the dipole center is z, I'd like to have a z squared on the bottom. So in order to do that, I'm going to have to multiply top and bottom by z squared here and here. So this is like, all this is like magic, okay? I'm just kind of copying my interpretation of what the book did. Okay, so multiplying top and bottom by z squared, I'm pulling the z squared that's on the bottom out to the front. So there's this z squared, there's this z squared, I'm putting it in the front. Okay, but the inside now looks a little different. The inside now looks like this. We have z squared over z minus d over 2 squared minus, not plus, minus, whoops, erased a little too much there. Let me rewrite this. Something crazy about my stylus. There should be a z squared down here. Things got a little corrupted there. Sorry. Okay. So it's going to be kq over z squared. Then we're going to have z squared over z minus d over 2 squared minus z squared over z plus d over 2 squared, closed bracket. All right. All right, next we're going to combine the fractions together. Okay? So actually I think I'll FOIL out the bottoms first and then combine the fractions together. So I have, I'm not going to have enough room if I do there. So I'm going to go kq over z squared, and then I have z squared over, and then the denominator is z squared minus, we have zd plus d squared over 4. That's a zd, not a 2d. And then we have minus, and then same idea over here, but it's z squared plus zd plus d squared over 4. And then combining the fractions together, we multiply the top of the first fraction by the bottom of the second and vice versa. So we end up with z squared times z squared plus zd plus d squared over 4 minus z squared times z squared minus zd plus d squared over 4. And all of this is over a common denominator, z squared minus zd plus d squared over 4 times z squared plus zd plus d squared over 4. So it's all very complicated. I need to edit this part, just this part that's on the screen right now. I need to delete this and fix this part. Okay, so I'm going to pick it up from this stage. So the first thing I'm going to do to clean this up is to pull out the kq. All right, so this gives me, we have 1 over z minus d over 2 squared minus 1 over z plus d over 2 squared. Okay. All righty. Change my bracket there. Okay. The other thing I want to do is kind of weird. I'm going to FOIL out the bottoms like this. So it's 1 over z squared minus zd plus d squared over 4. And then minus 1 over z squared plus zd plus d squared over 4. And then I'm going to factor a z squared out of the bottom. Okay, the reason I want to do this is because ultimately I'd like a z squared on the bottom. Z is the distance to the center of the dipole, and we always have like the r squared on the bottom, you know. And since z is the important distance in this problem, I'd like there to be a z squared under that kq out front. So that seems like a weird thing to ask for, but that's what I want to do. So I'm going to start that process by factoring a z squared out of this trinomial, which is going to give me 1 minus d over z plus d squared over 4z squared. And then same thing here, but it's z squared 1 plus d over z plus d squared over 4z squared. Okay, this way I have a sort of a z squared separate on the bottom, and we're getting rid of these denominators. Okay, I'm going to pull that out to the front and put it under the kq. So this is already looking like a field, it's KQ on top, distance squared on the bottom. Okay, and then, that's just sloppy, sorry. So it's KQ over Z squared. All right, so inside, what do we got? Well, we still have the 1 over 1 minus D over Z plus D. So basically I have these green things, right? These horrible green things, that one and that one. But those are both perfect square trinomials. Took me a minute to see that, but this one is just, whoops. This one is just 1 minus D over 2Z quantity squared. And this next one is 1 over 1 plus D over 2Z quantity squared. And then I'm going to combine these into one fraction. So multiply the, first one by the bottom of the second, and then the second one by the bottom of the first, and so on. So basically you're going to end up with something like this. 1 plus D over 2Z squared minus 1 minus D over 2Z squared all over 1 minus D over 2Z quantity squared times 1 plus D over 2Z quantity squared. Okay. It's pretty messy, huh? Alrighty. Now, if you combine like terms on top, it might be easier to think in terms of A's and B's. So anytime you see a 1, think A. Anytime you see D over 2Z, think B. So this is like, the top is like A minus B, A plus B squared, but you're subtracting, A minus B squared. So let's work that out at the top of the page. It'd be A squared plus 2AB plus B squared minus, and then A squared minus 2AB plus B squared. So what happens is the A squareds and the B squareds cancel, but you end up with a 4AB. So that numerator then is going to be literally a 4AB, which is 4 times 1 times D over 2Z, which is really 2D over Z. So that's just 2D over Z, that whole numerator. All right, the bottom, if we think in terms of A's and B's, it's a little different. Let me do a little more erasing here. I need a small eraser. If you think of A as 1 and B as the D over 2Z, it looks more like this. We have A minus B squared times A plus B squared. So let's take that to the top of the board and see what that means. A minus B squared times A plus B squared. You might think I'm going to FOIL that out, but no, I don't really dare to. What I'm going to think of it as is something all squared. A minus B times A plus B. So that's A squared minus B squared squared. See that? It's difference of squares on the inside, and there's a square on the outside. So it's A squared minus B squared squared. So putting back in the 1 and the D over 2Z, it looks like this on the bottom. It's 1 minus, so 1 squared is 1, minus D squared over 4Z squared all squared. Okay? All right, so I'm going to copy that, find a little space and copy that conclusion. And although it was a lot of algebra, it did pay off because it's so simple compared to what I had. Oh, and I forgot to write the little Z squared. Remember there's a Z squared on the bottom there and there? I forgot to write that here. Okay. You'll notice there's another Z on the bottom of the top, and that can be combined with the Z squared that I have on the bottom there. So I'm going to write actually with a Z cubed on the bottom. And then there's this other junk, which is 2D over 1 minus D squared over 4Z squared squared. And this is the field you experience standing on that line. This is the field you experience standing on that line. So this is the total net field. It's a magnitude, of course, but it includes the slight negatively directed field from the leftmost charge, and it includes the stronger rightward pointing positively directed field component from the right-hand positive charge. Okay? So I'm just going to draw a little picture again to remind you that this was a negative, this was a positive, this was the distance d, and we're standing z units from the center over here. So if you want to know what the field is standing over there, you would use this formula. Wow, look at that. Pretty crazy, huh? All right, now you'll notice something just popped up in our work. There's a little cutie. Isn't he a cutie? He's a cutie. That cutie can be abbreviated P. P for dipole moment. Dipole moment. Okay? So we end up with K cubed P, and there's a 2 there. And then there's the Z cubed. I'm bringing the 2 out to the top left this time. And this is all over square root of, not square root of, square of 1 minus d squared over 4z squared, quantity squared. Okay, so that was a lot of work. Now, there's another advantage to writing it this way. There's another advantage. Suppose you stand really, really far, far away, so that z is much, much bigger than d is. So, d might be a foot apart, so like the 2 charges are a foot apart, but you're standing a mile away. You know what I mean? Or maybe maybe it's electron-positron pair, and you're standing an inch away. Either way, z would be so much bigger than d. I didn't mean to write z is greater than or equal to d. I meant to write z is greater than d. Usually we use like a double greater, just double, not triple. Z is much bigger than d. This is how it's written. Or you can say that z over d is almost, really large. You can say it's really large. You can say d over z is super, super small. Right? It's very, very small. That's another way to say it. What happens then? Well, if that's the situation, then this term is going to vanish. This little bottom right piece. So it's going to basically just become a 1 right here. Just a 1. So that's a nice, if z is much, much bigger than d, then you can just say that the net field is only the 2k cubed p over z cubed. Like, you don't need the rest. And since often our dipoles are, far enough away, we could use this abbreviated formula. Okay? So don't forget about the blue formula above it, but understand when you're further away, you could use this abbreviated form. And the last thing I want to say before we move on from this is I just want to remind you that, and I mentioned this very briefly one day, k is sometimes written as 1 over 4 pi epsilon naught. And so you might see it written that way instead. And if you substitute that expression in for k, it does change the way the formulas look, all of them. Field, force, electric field of a dipole, like we're doing here. Okay? But just know that k and 1 over 4 pi epsilon naught, they're the same thing. Okay? They're the same thing. And by the way, epsilon naught is 1 over 4 pi k. Like, you could switch the k and the e naught around. We'll talk about what epsilon naught means later. It's called a permittivity constant. Okay, it's not too relevant this moment. So I'm not really focusing on it too much. Let's go down now to our next topic. Continuous charge distributions. Continuous charge distributions. Okay, so thanks for sticking with me through that long and tedious calculation of our first compound object, the electric dipole. Now, what about other arrangements of charge? Suppose you don't have like a positive one, a positive charge and a negative charge combined together, like into this dipole, but suppose you have like thousands and thousands of charges. Well, there are some distributions we can handle pretty well in this class. One of them is a ring of charge. So like if we stack charges into like a ring, like this, to form like a wedding band, we could find the field produced by this compound object. Okay? But we'd have to kind of measure, I think, kind of along the axis of symmetry. Okay, so we like stand here and try to say, okay, how much field do we feel here? All right, or how much field is present here? Even if we can't feel it, we know it's there because of this aroma idea. Or maybe like a really long, like large sheet of charge, like it's all neatly organized on here, and then you're like standing above it, and you're like, oh, okay, what's the field I sense up here? Okay, so anytime we do that, that's called continuous charge distributions. And anytime you're trying to find the electrical field due to a continuous charge distribution, you do it by treating every charge element as a point charge, and then you start summing up all the electric field vectors by all those charges using integration. So I know some of you haven't had BC calculus yet, or even calculus enough to where you can integrate. But I think you'll find that our integrals are actually pretty easy to do. Like the actual math of the integration process is pretty easy to do. So don't stress out about that. There's an introductory concept before we can study continuous charge distributions. We have to understand that mass density is called rho, right? And we measure it by doing mass over volume. This is an old, 8th grade concept. You take kilograms, you divide by cubic meters, and you get your density. This is the Greek letter rho, and it's often used for density, but not always used for density. Okay? Now, we have an issue. Sometimes we have a ring, or sometimes we have like a line of charges, right? Oh, I'm sorry, I should have said something up front. We won't be studying mass density per se, but we'll be studying charge density. So think of it in terms of coulombs per cubic meter. So like how much charge is present in a given amount of space. So we're going to call that charge density, okay? So I did want to mention mass density because I knew it was something you'd seen before, but charge density is instead of mass over volume, it's charge over volume. Okay, so we have basically several possibilities. If we're working with a one-dimensional scenario, then we only have to consider how much charge there is in a particular given length, right? So there might be Q amounts of charge in this distance, L. From here to here is L, right? Or perhaps we would have like a surface covered in charges. And then we would want to think more in terms of area. So we'd be like, okay, let's grab that bit of area. How much charge is there in that area? So that'd be like charge over area. Okay? Or perhaps it's a three-dimensional thing, and it's like a box full of charges. And they're all throughout the box. And in that situation, you want to circle like a little volume within there and say, okay, how much charge is in this three-dimensional space? Okay, so we have three types of density. We have linear charge density, which we often use a lambda. That's good because lambda starts with L and linear starts with L. So it's linear, it's a nice straight line of charge, like this. And it's just simply defined as how much charge there is divided by how much length you have. So if you're dealing with small amounts, and this is one thing I don't agree with physicists on, they like to call a small amount of charge dq and a large, small amount of distance dl or ds. I think they use dl. Let me check on that. I'm sorry, they like to use ds. We talked about this in calculus class. We don't really like to think of a small amount of charge as dq. We like to think of an infinite dissection of q as a dq. So technically nothing's infinitely small here. The smallest thing we have are the elementary particles, maybe quarks or something like that. So none of this gets infinitely small. I don't like the lowercase d being used here, but our book does it, so I'll do it. But think of dq as a very small delta q. Okay, so this is called linear charge density. How much charge is there in a tiny amount of space, ds? Okay, dq is the tiny amount of charge, ds is the tiny amount of distance. Okay, so normally we would write that as dq equals lambda ds. So it's not really differentials, it's the really deltas technically. Okay, the next one is that surface idea I was mentioning earlier. You pick an area and you look at it. So this is lambda equals dq over ds. All right, surface charge density. Okay, so for that we don't use lambda, we use something that sounds like S in Greek, so it's sigma. So sigma, looks like a little Hershey's Kiss. So sigma is dq over dA. Remember I said that it's like a table full of charge and you're going to pick a little area, right, to look at, a little area. So we would say that dq is sigma dA. Okay, and dA just means it's a tiny bit of area, teensy-weensy small thing. The last one is, because it's very similar to what we do with masses, we'll just go ahead and use rho. Instead of something that starts with V or sounds like V in Greek, we'll just pick rho, which is what we used back in 8th grade physical science. So that's charge per volume, or you could say dq is rho dV. Okay, now that we have our three types of charge densities, anytime we see a dq, we can replace it with either lambda ds, sigma dA, or rho dV, depending on if it's a one-dimensional, two-dimensional, or three-dimensional situation. Now on to our first example of a continuous charge distribution. We're going to talk about a ring of charge. Imagine charges. Okay, and try not to think atoms. Try to actually think fluid. Okay, so imagine, I'm not going to go around. It takes too long to draw all the pluses. Imagine that there's all these plus signs going all the way around. And instead of thinking of it as individual protons, everything is so small and there are so many of them, you can almost think of each charge as divisible down to an infinitely small amount. Okay, so we're going to use the calculus ideas of integration to actually collect not an infinite number of particles, but such a large amount it feels infinite. So we're going to use integration even though technically integration combines an infinite number of things. Okay, so what we're going to do now is we're going to look at one little tiny strip. So just imagine stealing a tiny little strip. It would look like this. Okay, there's a tiny amount of charge on that thing. It's a tiny bit of length. So we're going to use that linear idea. We're going to say that dq is lambda ds. Okay? Okay, now what is lambda though? Lambda is the ratio. So it turns out we actually know lambda. This entire ring has a total charge q. Total charge q. And it has a total length going around 2 pi r, right? Because it's a circumference. So technically, lambda, as long as everything is uniformly distributed, one little sliver and the next little sliver should have the same amount of dq. So if you pick an identical ds somewhere, you should find an identical dq. Another way of saying that is that lambda is constant throughout this material, throughout this insulating material, or whatever it is. Okay, so lambda should be total charge over total length, if that makes sense. So I can say that lambda is total charge over total length, which is total amount q distributed over 2 pi r. I accidentally wrote 2 pi lambda. Okay, so now a quick substitution gives me that dq is q over 2 pi r ds. And this is going to go into our integral here in a few minutes. All right. Now there's an azimuthal symmetry. We talked about this in BC Calc after the AP test. In a cylindrical coordinate system, the azimuth angle is that angle when you go around the top, or somewhere inside, you're going this direction. This whole thing is azimuthally symmetric. So every single field vector is pointing away from, assuming this is a positively charged ring, every single field vector is pointing away from every single dq. So every tiny little dq is contributing its own field line, right? Okay, so you'll see something. Watch. If I pick this little ds over here, the field vectors look like this. The field lines poke out like this. And some are pointing kind of towards us, right? Some are pointing away from us. Some are pointing straight out of the board at us, right? But then if you kind of follow those up to point P, right, there's always another charge on the polar opposite. There's always another ds on the polar opposite that's sort of doing the same thing, right? So what happens is the field line coming from point A over here, which is the small ds on that side, and the field lines pointing out of point B, which is over on the right, kind of come together in the middle. And if you're just thinking components, we have a radial component and a height component. There's always an r and an h in every scenario, right? And h is actually z. It's already labeled for us. See? Okay, so what I'm saying is the radial components should cancel out, one canceling with the other. But the z components should combine because they're both pointing up, you see. They're both pointing up. So one's pointing radially in toward the center, the other's pointing radially in toward the center. Those are directly opposite. Those cancel out, but the two ups combine. So the only thing that ends up contributing as you go around the ring is the vertical component. Like all the radials cancel out because there's always one across from it. Just like at a large table at a party, you might have somebody always sitting across from you no matter where you sit at a round table, right? Okay, but that upwards component is not trivial, and they all combine. So it turns out all we have to do is look at the z component. Okay, I need to erase some of the scribbling I've done. Hopefully you're convinced now that the z component's the only component that matters, okay? So, you'll notice also that z is technically adjacent to theta. It's adjacent to theta, right? Which means that z is really rho cos theta. It's really rho cos theta. Okay, that's important. So remember what field is. So field is you take your charge, which, you know, in this case is dq, you slap a k on it, right? And then you divide by distance squared. So what exactly does P feel up here at the top? Well, up here at the top at point P, we sense the charge, the electrical field coming from ds, right? So the distance is clearly rho, that's on the bottom here, rho squared. The charge amount is dq, and k is there. So this is the charge, the field experienced up there at point P. But that's from one of the dq's. There's billions of dq's, and we already said that the fields only matter in the z direction. So if we slap a cos theta on here, what happens is that gives us just the upwards piece, if that makes sense. Just the upwards piece. So now, is this the whole field? No, this is just a tiny piece of field. Okay, so this is what we call a differential field element. Okay, it's not really a geometric thing. It's just, if you're looking at a tiny amount of field, it's going to be k times a tiny amount of charge divided by a distance times cos theta to ensure that we only get that vertical component. So here's the beauty of it. The rest is pretty easy. You're going to integrate all the dE's to get the E, right? You collect all the little guys to get the total field, right? So I wrote that down below here. It says E is equal to the integral of dE cos theta. And I probably should have called this part dE, because this is the total field. dE sub z is dE cos theta. So let me draw a little triangle here. I should draw this in the first place. dE is a vector field. It's like a tiny little vector field. And there's a theta here. All right? dE is actually directed along the hypotenuse. But this part is dE cos theta. You might call that like dE in the z direction. And this is dE sine theta. Right here. This is dE sine theta, this blue thing. But nobody cares about dE sine theta. Even though that's the radial component, you might call it dE sub r. Nobody cares about it. So we don't want it. We're just going to focus on dE cos theta, also known as dE sub z. All right, so hopefully I didn't confuse you there. We're going to be integrating the dE cos thetas, and we already said up above, so only vertical components, only E sub z. Oh, right here, only k dq over rho squared cos theta contributes to any field at any given point. Okay, I'm sorry, I'm getting a little distracted. Right down here at the bottom, we're going to go ahead and integrate. So we have k dq over rho squared cos theta. That's our dE, we said. All right, scroll down. Earlier, we said that dq is lambda ds, remember? And lambda was total charge over 2 pi r, total distance. So that's going to get inserted where it says dq. So this is going to be q over 2 pi r ds. And then there's a cos theta there, and this is a rho squared. What are we integrating from and to? Well, notice our differential is ds, right? Our differential is ds. So we don't really need this comment here. Our integral is over ds. So s basically goes from 0 all the way around to 2 pi r, right? So s can be, we want to collect all the way from 0 to 2 pi r. So that's what that's going to be. Also, the cos theta can't be there. I mean, we don't want thetas involved, actually, if we can help it. So what I'm going to do is to get rid of this cos theta, I'm just going to go back to this triangle we had earlier. this was r, this was z, and this was rho. It's in the triangle up above. It's also should look very familiar to my Calc BC students from last year. So when I say cos theta, you could just think, z over rho. So that's what I'm going to replace this with, z over rho right here. So that's more of a geometry thing, but it does kind of bring back down the number of variables. So we're going to end up with, and let's see, we have k, q, 2 pi. All right, and then we have integral, and then we have a ds. We just put in a z over rho, like 2 seconds ago. And then this is all over rho squared. So I did pull out a couple things. Oh, and then there's also an r here. So I think I got everything situated. Alrighty. So there is a rho cubed going on. So I'll write that in. So it looks like E equals kq over 2 pi. And then it's, think of it as ds, and then there's a z, and then there's an r rho cubed, like that. Okay. Oh, and by the way, I used a lowercase r. They used an uppercase r on their triangle, so we should probably fix that real quick. That's on the drawing. That was an uppercase r. So I'm just going to go back and put in an uppercase r there. So that uppercase r and that z also, those really don't change, right? Like those are properties of the triangle no matter where you're standing on the charge ring. So as you go around the charge ring all the way around, right, r is this from the center out and z is the distance up. So that never changes no matter where you're standing. So I could pull those out of my integral too. So I have k, q, z over 2 pi capital R, I said. And then you're integrating just ds. Oh, and rho cubed. Rho cubed can pull out because the charge density is constant all the way around the ring. You find the same amount of charge for every little segment you look at. Okay, so what are we integrating from into? We're integrating from minimum possible ds, which is 0, all the way to maximum possible, which is 2 pi r. So the antiderivative is going to be super easy. The integrand is literally 1. So what is the integral of 1 ds? Just s. Then you plug in the 2 pi r and the 0, and you subtract, and you just get 2 pi r. Okay, so that's going to give me, over on the left, I'm going to write my answer on the left. I have kqz over 2 pi r times 2 pi r. Again, I forgot to use the capital R on my upper limit of integration, sorry. And then there's that rho cubed on the bottom. So the 2 pi r's cancel, and we get kqz over rho cubed. I'm sorry, when I pulled the rho cubed out, I explained it wrong. The rho is not charge density, it's the distance to the point z. So anyway, I misspoke that, but that too does not change. This quantity right here, at the bottom here, the rho cubed, it represents not charge density, but rather just simply the distance to point P. All right, so anyway, sorry if I confused you there, but the integration was actually pretty easy in the end. We just did an integral ds, which is just 1s, and then you do from 0 to 2 pi r, which gives you 2 pi capital R. Okay, so because we may or may not know rho, we may know maybe r and z instead. You could use Pythagorean Theorem to write this one more time. So I'll do that. Technically, the rho here is the square root of r squared plus z squared. So you could also write it like this, kqz over, and then r squared plus z squared to the 3 halves. And this is the net field experienced at point P directly above a charged ring on the axis of the charged ring. Okay? So there you have it. Our second